Okay guys, this next video here kicks off chapter 5, which deals with thermochemistry, and we are going to be covering some of the basic ideas involving energy. So in this first section, we are going to talk about what energy is and different types of energy. And then, we'll also talk a little bit about heat and temperature and thermal energy. And we'll save this last part here dealing with heat capacity and specific heat for the next video. So this chapter comes from the broader subject of thermodynamics, which is a study of the macroscopic relationships between heat and other forms of energy. So we're not thinking about things at the molecular level. We're thinking at the macroscopic level, the human level, and we're talking about heat and other forms of energy. Thermochemistry is a branch of thermodynamics where one studies the heat and the energy that can be released or absorbed in chemical reactions. And so just to give you a few examples, our bodies, for example, we derive energy from the foods that we take. When we are traveling in our vehicles, we are burning some type of fuel that produces heat. And I'm not exactly sure what's going on here, but it looks hot to me. And so certainly there's some energy being involved in whatever this picture is here on the right. On the next slide here, what I've included are some basic definitions that are helpful to think about before you start discussing thermodynamics. So in thermodynamics, we often talk generically about the system, that is the system of interest. And so the system refers to some portion of the universe that you find interesting to study. In chemistry, the system is usually some reaction mixture of interest. Another term that we use is the surroundings, which refers to everything else in the universe that we don't really care about. And so very often we make a diagram that looks something like this. So this is a generic system of interest that is surrounded by its surroundings. And so this is the portion of the universe that we care about. Everything else is the surroundings. In thermodynamics, we are interested in characterizing the state of the system. Okay? And what the state of the system means is that you have a complete specification of the system's macroscopic properties. Sometimes we call these variables. For a gaseous system, for example, we would typically talk about pressure, volume, number of moles of gas, and the temperature of the gas. And so these are examples of system variables that we would be interested in knowing. These different variables can be characterized as either extensive, which means that they depend upon the size of the system, or they may be intensive, that is, independent of the size of the system. Okay? And so I'm going to be using the terms extensive and intensive throughout the rest of the chapter, and so I wanted to explain what I mean by these terms. So we are going to try to classify all of these different properties here as being either extensive or intensive. And so this is a little on-the-slide example that we're going to think about. So the way that you determine whether or not a variable is intensive or extensive is you imagine taking your system and doubling its size. So you take your system, you make an exact copy of the system, and then you bring those two systems together to form a double-sized system. And then you ask yourselves, does the quantity that I'm thinking about change? So with respect to temperature, imagine that you've got a glass of water at room temperature. and then you make a second glass of water. Everything's identical about that second glass of water. Well, now imagine pouring the 2 glasses of water together and ask yourself, does the temperature of the water change? Hopefully you've said no, and that's correct because temperature is an example of an intensive quantity. It is independent of the size of the system. What about pressure? Pressure is kind of a tricky one. Imagine that you've got 2 rooms connected by a door, and the door's closed. In one room, the pressure is 1 atmosphere. In the other room, which is identical in every way, the pressure is also 1 atmosphere. Do you expect a pressure change if you open the door between the 2 rooms? Sometimes people say yes, sometimes people say no, the pressure won't change. The correct answer is the pressure will not change because pressure is an example of an intensive variable. It does not depend upon the size of the system. Mass is a bit easier, right? If you take a glass of water and you double the amount of water in the glass, the mass will increase. So mass is an extensive quantity. It does depend upon the size of the system. What about volume? Well, if you take that volume of water and you double it, the volume is also going to double. So volume is an example of an extensive quantity as well. Density is a fun one. Density, as we know, is defined as the mass of the system divided by its volume. Okay, so here you have 2 extensive quantities. Well, what if you doubled the size of the system? You would double the mass and you would double the volume because mass and volume are extensive. Notice that the 2's cancel out and you're left with the same density. So density is an example of an intensive quantity. In fact, whenever you take the ratio of 2 extensive quantities, the result is always an intensive quantity. We'll take advantage of that in this chapter as well. Oh, for the last one, it's kind of tricky as well. Energy, and I don't even know what symbol to use. I'm just going to use the symbol U, which we will use for the internal energy. And I'm just going to tell you the answer. Energy is an extensive quantity. The energy is a property of the system, and the amount of energy that the system has depends upon its size. If you double the size of the system, you're going to double the amount of energy in it. Okay? So that's intensive versus extensive variables. We'll be using that term as we go in this chapter. Okay, let's talk more about energy. So the standard physics definition of energy is that energy represents the capacity of a system to do work. That's why we say that it's a property of the system, because if the system has more energy, then it can do more work. And I've tacked on to my own thoughts on this. Energy is the capacity of the system to do work or produce heat. In fact, you can make the argument that those are the same thing. Doing work and producing heat are similar, but I like to include both of them. So energy is the property of a system. The SI unit of energy is the joule, the capital J there for the symbol. A joule is equal to a Newton meter. And if you express newtons in the base SI units, you get 1 kilogram meter squared per second squared. So 1 joule is equivalent to this combination of base units. In some literature, you will also find non-SI units. For example, the calorie, lowercase c. 1 calorie is equal to 4.184 joules, and that is an exact conversion factor. In nutrition, the calories that we associate with our food, those are actually kilocalories. Or the calorie with a capital C is 1 kilocalorie, and that's equal to 1,000 little c calories. Energy comes in different forms, and I'm sure you've seen this before. Kinetic energy is the energy that we associate with the motion of an object. So here this E subscript K, where the K stands for kinetic. If you have an object with some mass m that has some speed v, the kinetic energy is given by 1/2 times the mass of the object times its speed squared. So kinetic energy is the energy associated with how fast an object is moving. It's also related to its mass. Potential energy is another form of energy. It is the energy associated with the position of an object, typically in some force field. For example, a gravitational field. Let's suppose that you have an object of mass m that is some height above the surface of the Earth. G is the acceleration due to gravity. This is how you calculate the potential energy associated with that object's height. And on Earth, the gravitational constant is 9.81 meters per second squared. In the pictures here, we have a lovely waterfall. The water in the river is moving, and it has a high potential energy up at the top of the waterfall. As the water falls, it loses potential energy, but it gains kinetic energy. That is, it starts moving faster and faster and faster till it hits the bottom again, where it's at the same height, till it's at a new height above the surface of the Earth. You can actually exploit this conversion of energy using a hydroelectric dam. And so here, water is dammed, the river is dammed up at the top where it has a high potential energy, and then if you release the energy, if you release the water slowly through, or not slowly, but if you release the water in a controlled way through a set of turbines that you can make spin, you can then convert some of that kinetic energy of the water, or the potential energy of the water, into electric energy, which you can then use to power your electrical grid. So here we have just a couple of simple little problems, just calculating, it looks like kinetic energy to me, so let's go ahead and work these just for fun. So a baseball pitcher can throw a baseball so that it travels between 60 and 90 miles per hour. A regulation baseball has a mass of 143 grams. And let's suppose that it's thrown at 33.5 meters per second. What is the kinetic energy of that baseball in joules? Well, if you put all of your units in SI units, then the output will also be in SI units. So let's calculate this kinetic energy using the kinetic energy formula. Recall that the kinetic energy of mass is the kilogram, not the gram. So we are going to take this baseball to be 0.143 kilograms, okay? And then we're going to multiply by the speed in SI units, which is that 33.5 meters per second, and we need to square that guy. And so we'll run this through our calculator. Take the 33.5, we'll square it, and multiply by 0.143, divide by 2, and I'm getting 80.2 kilograms meters squared per second squared, which is equivalent to the joule, right? So that unit, kilogram meters squared per second squared, is equal to a joule. So 80.2 joules. Oh, let's see. At midnight, my notifications turn on, so that's why that keeps happening. An electron whose mass is 9.11 times 10 to the minus 31 kilograms is accelerated by a positive charge to a speed of 5 times 10 to the 6 meters per second. What is the kinetic energy in joules and calories? Looks like I forgot to do that conversion here, but I'll do it on the second one. So the kinetic energy of the electron, again, 1/2 mv squared, 1/2 times the mass of the electron, times 10 to the minus 31 kilograms. And then the speed, very fast moving electron here, 5 million meters per second, which we want to square. We'll square that, multiply by the mass, and divide by 2. And so I'm getting 1.14 times 10 to the minus 17. That's going to be joules. The reason it's so small is because the electron has such a small mass in this case. How do we convert these to calories? Well, we use the conversion factor that 1 calorie equals 4.184 joules. So let's go ahead and take the 80.2 joules. So 80.2 joules. We want calories in the numerator and joules in the denominator. The joules are going to cancel. And we get 19.2 little calories. Okay, you could do the same thing with the joules for the electron, but I'm gonna go ahead and leave that to you as an exercise if you wish, and we'll move on to the next item. So this is just a discussion question. We have a solar-powered water pump whose photovoltaic cells are on the top panels. These cells are responsible for collecting energy from the sunlight. They store it for a moment in a battery, and then later that battery is used to drive an electric motor, and that motor will then pump water up into a storage tank. They want to know what energy conversions are involved in this process. Well, so you have electromagnetic energy in the solar light. That is then transferred to the electrical energy within the photovoltaic cells, where it's stored in the battery. Then the electricity from the battery, or the potential energy within the battery, is then used to drive the motor, which means that it's being converted, that potential energy is being converted into kinetic energy that moves the motor, which then in turn moves the water up the hill. So you have radiant energy from the sun is being converted into electric potential energy. Then that electric potential energy is being transformed into kinetic energy of both the motor and the water that's being pumped out of the storage, pumped up to the storage tank on the top of the hill. Let's see. I think here this is. Let's see. Yes, I think this is going to be our last slide of this topic. Thermal energy and temperature. They sound similar, but they're actually different quantities. They're related to each other, though. So thermal energy is the kinetic energy of all of the atoms and molecules within a given system. So the molecules of any object you like, so let's just call it a gas. So the molecules of a gas are bouncing around. They have kinetic energy. They move in seemingly random directions, right? All of the gas molecules are moving around in different directions, and they're colliding with one another and colliding with the wall. This kinetic energy of all of the molecules is what we call the thermal energy. Temperature, as you know from experience, is a way of quantifying what we regard as hot or cold. Okay, it turns out that the temperature, while not the exact same thing as the thermal energy, is proportional to the thermal energy of a sample. That is, the temperature is proportional to the kinetic energy of the atoms and molecules within a sample. And so the hotter the object is, the larger its temperature, the more thermal energy the sample has and the faster the atoms are moving. And so that's represented in this cartoon here. If you have a colder object, that means it has less thermal energy. That means the molecules are not moving as quickly on average. They have less kinetic energy. Substances tend to expand and contract as their temperature increases, and that's the basis of thermometers. In fact, they expand and contract in a regular way with respect to their amount of thermal energy. So, for example, a liquid in a thin capillary here, its density increases as you increase the temperature. And so if you have a fixed mass of liquid in the capillary, as you raise the temperature, then the volume of the liquid is going to increase. So as the temperature goes up, the volume goes up in a regular way. And so you can use that to quantify the temperature of anything in contact with the thermometer. Here's another example. This one involves the expansion of metal wires. In fact, if you have two different metals that you attach to one another and then wind them around in a coil, the two different metals expand differently as their thermal energy increases, which causes the wire to either expand or contract like a spring as a function of temperature. And you can use that as a gauge of what the temperature is. So we're going to stop this video here, and we're going to pick up with heat and heat capacity in the next video.